Hello everyone. So I start the next part of the lecture on nuclear reaction mechanism by discussing much more details about the compound nuclear reaction. Just to give you examples of the compound nuclear reactions, like neutron capture reactions are a very fine example of compound nuclear reactions. When the neutron is captured by the nucleus, it is amalgamated with the nucleus and the compound nucleus is excited to an excited state that excitation energy will be equivalent to the binding energy for the thermal neutrons. So essentially excitation energy is ECM plus Q. Q value is for the neutron capture reaction is the binding energy of the neutron in the compound nucleus. And if you take thermal neutrons, then the spectral energy is close to zero. So that is why in the case of thermal neutrons, you can say excitation energy equal to the binding energy of neutron. And the angular momentum that is given to the compound nucleus will be target nucleus plus the neutron spin. So neutron spin is half and target nucleus for cobalt-59 is 7/2. So 7/2 plus minus half. J of the compound nucleus can be 7/2 plus half or 7/2 minus half. Whatever is the state of the excited nucleus is available, that will be populated because angular momentum has to be conserved. So we will discuss the decay of a compound nucleus in terms of the available excitation energy and the angular momentum. These are the two important properties which will govern the ultimate fate of the compound nucleus. In the case of charged particle induced reaction, as I discussed earlier also, so the charged particle will bring in some energy because you have to cross the Coulomb barrier of the target nucleus. So the same example I discussed earlier, we calculate the Coulomb barrier for this 1.44 Z1 Z2 by R0 a raised to 1/3 plus A2 1/3. So let us say for alpha on niobium 93 Coulomb barriers we can calculate 13.8 MeV. And the Q value for this reaction will be mass of alpha plus mass of niobium 93 minus mass of technetium 97. You can again put the value, delta M value, and you get 2.437 MeV. So you have to have the energy, the center of mass energy of the alpha more than or equal to 13.8 MeV. Normally you will be much above the Coulomb barrier. Let us say you take a 30 MeV alpha beam, and for a 30 MeV alpha beam, again calculate what will be the excitation energy and angular momentum. So the excitation energy of the compound nucleus will be ECM plus Q. For 30 MeV, ECM will be 30 into 93/97. So here you take the masses, actual masses, because it is not the difference in the masses that the A will get cancelled out. So when you are calculating center of mass energy or required energy, you take the mass number. Mass numbers are very close to the masses. So you take here actual mass numbers plus Q value, that is 31.2 MeV. And the angular momentum, now the projectile can bring in a large range of angular momentum from 0 to Lmax. And so there is a distribution of angular momentum in the compound nucleus. Unlike in the case of neutron-induced reaction where you have only one spin populated, you have a distribution of angular momentum, and that distribution is given by 2j plus 1 exponential minus j plus 1 upon 2 sigma square. So that is like a complete distribution of j values from 0 to some max value. So these are the two properties we will be discussing more, how the compound nucleus will decay. So I will now discuss the compound nucleus behavior in two regions. As you know, this is the compound nucleus. I have now again shown here the formation of a compound nucleus by two different reaction groups, alpha on boron 10 and deuterium on carbon 12, forming nitrogen 14 at the compound nucleus. Now for the low mass projectiles and target, you will find that the excited states, see this you can equate to like cell model states. So there is a large gap in the excited state of this nuclei. So if you populate a compound nucleus when the excited states are discrete, they are well separated from each other, then that particular, suppose you populate this state, then the subsequent decay of this excited compound nucleus will be governed by the width of this level and the available states in the product nucleus. So it can emit a proton to form carbon 13. So this, when you populate a compound nucleus in discrete states, we call it as a resonance region. That means you can achieve resonances in the cross sections whenever there is a population of a particular energy state of the compound nucleus. So this is what I have tried to explain here, that for two different reactions, you can populate the same state of a compound nucleus, which can then decay by another channel to the heavy residue and the particle that is emitted. And there can be now even gamma emission from the excited states of carbon 13. So that will give you resonances in the gamma ray as a function of projectile energy. So what you do, you measure the gamma ray yield, vary the alpha energy, you measure the gamma ray yield, vary the deuteron energy, and you will see these gamma rays in the spectrum. What these people found out is, in fact, it has been done quite early in the 1950s or 60s. It was found that the characteristic gamma ray spectrum and their yield are independent of the which way the compound nucleus was formed. Both these reactions, alpha plus boron and deuterium plus carbon 12, give rise to the same energy states. So again, in the resonance region, where you populate a nucleus in a discrete state, there are resonances in the cross section also of the compound nucleus, and there are gamma spectrum also shows the resonance. So this is the kind of experiment that have been done to prove the independence of the compound nucleus reaction formation and decay, and subsequently I will see even in the continuum region. So here actually I try to explain here the width of this level is much less than the spacing between the levels. You go to still higher and higher energy, the width of this level become more than the spacing between the levels. So the spacing between the levels are low, then they will start overlapping, and you see what is called as the overlapping levels will be looking like a continuum. So the continuum, now we cannot apply the discrete states formalism, where we apply there the statistical model formalism. So this was for the resonance region, and now we come to the continuum region, where the energy states, the gap between the excited states is decreasing as you go up and up. So finally, what will happen? The spacing between the states becomes so low that they will overlap, and then you will see a continuum region. It is like it's like a Fermi gas. A Fermi gas where you have all the nucleons are populating states which are overlapping. So they gives you like a feeling of a Fermi gas moving in a particular chamber. So the projectile plus target nucleus, like charged particle induced reactions, when you populate the nucleus, typically the binding energy of the nucleon will be around 7-8 MeV. If you populate a nucleus more than that energy, invariably you will end up with the overlapping states, and that will be the continuum region. So for the continuum region compound nucleus, you apply a statistical model. You cannot count the individual levels. So what you talk about the density of the nuclear states. So you don't have how many levels are there. Like here you can count how many levels are there in one electron volt or 1 MeV. But in the case of continuum region, so you apply a level density formalism. This is called number of levels in a particular unit MeV energy, dN by dE equal to rho E, that is the level density, and it is given by the Fermi gas model, a parameter constant exponential to A E star, where E star is the excitation energy, and A is called the level density parameter. So basically, the level density parameter is a measure of what is the number of levels in 1 MeV. So that is a measure of that. So it is always associated with the level density. So this level density parameter is related to the excitation energy of the compound nucleus by a term called temperature, as a nuclear temperature. So when we have an excited nucleus, we say it has got certain temperature, and this temperature part becomes very important. We will see later on. You can hear I try to give a value of temperature. So nucleus is hot. It is excited. It is hot, but the hot is so hot that the temperature, you get a feeling of the temperature here. So the temperature corresponding to 1 electron volt excitation, we can relate the temperature to kT in terms of Kelvin. K is the Boltzmann constant, and this is given by 8.617 10 power minus 5 electron volt per Kelvin. So if you calculate the temperature corresponding to 1 electron volt, 1 electron volt upon this much electron volt per Kelvin, 1.16 to the power 4 Kelvin. So if you have a nucleus and excitation energy of 1 electron volt, then it has got a temperature of 10 power 4 Kelvin. So 1 electron volt will be close to nearly 0. You populate at 1 MeV and straight away 10 to the power 6 into 10 to the power 4 10 to the power 10 Kelvin. So that if you recollect the nuclear fusion, we are talking about 10 to the power 8 Kelvin, that is about 10 to the power 4 electron volt. So tens of keVs. So this is where you try to correlate temperature of the nucleus, which is behaving like a hot Fermi gas. So this is like a pressure cooker where you have a gas molecules at very high temperature. And so we deal with the excitation of a excited nucleus as if it is a Fermi gas at high temperature. So we will try to see what are the signature of the decay of a compound nucleus which is having high temperature, which is having high angular momentum, and this formalism of Fermi gas. Again, the cross section for a reaction A going to A comma, that A comma B is B. So A and A form a compound nucleus, and the compound nucleus is emitting by a particle B and left with residue capital B. So you have the formation of the compound nucleus and you have the decay of the compound nucleus, two steps which are independent of each other. So let us try to see the probability of decay of the particle to the residue. Now, depending upon the energy of the particle, it can populate different energy states of the residue. So what we essentially measure is the spectrum of this particle B, and if it is a compound nucleus formation, what type of decay the spectrum the particle will have, that we are trying to see here. So the maximum energy of the projectile, that is small b, is given by the excitation energy. Let us say it is found here, E star minus the binding energy of the particle in this nucleus. So that is called the suppression energy or the binding energy, because binding energy is the energy required to remove a nucleon from the nucleus. So this much energy we have to supply. So excitation energy minus binding energy is the maximum kinetic energy of the particle. So here SB is the suppression energy of particle B in compound nucleus. So the excitation energy of this residual nucleus will be now compound nucleus excitation energy minus the binding energy of particle in the compound nucleus minus the kinetic energy of the particle that is coming out. So these are the four energies involved. When the particle is emitted from compound nucleus, energy equivalent to the binding energy is required, and so this residual nucleus may be populated in the certain energy states, and that excitation energy is given by this formula. So the probability of decay to the particular energy state of the daughter residue depends upon this excitation energy. Higher the excitation energy, higher will be the level density. So basically, why depends upon E star? Because level density depends upon E star. So the probability of decay of B to a particular energy state depends upon the rho EB, rho level density of the residual nucleus at a particular energy, that is given by this e to the power 2 root AE. And you can now explain this EB. So you can substitute this A in terms of AT square equal to E star. So A equal to E by T square. E by T square. And so you can substitute here E star by T square into E star alleyway there. So EB square upon T square, square root. So it becomes EB by T. So we have taken care of the level density parameter, which we do not know. So the probability of decay of B to the residual nucleus is exponential of 2 EB star upon T, where T is the temperature. And we do not know the E star. What we know is the binding energy of the particle in the nucleus, the kinetic energy that we measure, and the initial energy. You can substitute E star B in terms of compound nucleus E star minus kinetic energy minus binding energy. So the excitation energy of the compound nucleus is known. The binding energy of the particle in the nucleus can be calculated. So they are constant terms. So it becomes variable term is the particle energy. Particle energy upon temperature. So the probability of decay of the compound nucleus into the residual nucleus in certain states is equal to proportional to E raised to minus EB upon T. Where is EB? Epsilon B is the kinetic energy of the particle. So you will find that as a function of EB, the probability of decay will be, this is called as the max. There is some pre-exponential term, root of EB, which I will not explain, but it is the pre-exponential term followed by the E raised to minus. So this term is E raised to minus epsilon B upon T. And from the slope of this, actually, you can find out the temperature of the nucleus when it is hot. So this is called the Maxwellian nature of the particle spectra. So if a nuclear reaction happens and the particles that are being evaporated by the compound nucleus, they follow this pattern, we say this is the signature of compound nucleus. So one of the signatures of the compound nucleus is the Maxwellian nature of the particle spectra. Okay, so how does the compound nucleus decay? You have an excited nucleus having certain excitation energy and angular momentum. It has got different pathways for the decay, like neutron, proton, alpha, even gamma ray emission can take place. And if it is a heavy nucleus, can even undergo fission. So there is there are different probabilities for de-excitation of a compound nucleus. And as I mentioned previously, it depends upon the available channels. So you have excitation energy, you have an angular momentum. That nucleus to decay, you have different options: particle evaporation, gamma emission, and fission. So whichever process can carry away the large amount of angular momentum and excitation will be more favored. I'll try to explain here by this diagram here. So if you recall, the compound nucleus has got two parts. One is the excitation energy, second is the J here. So here is the angular momentum population I have given here, 2L plus 1 TL. That's what I have to give here. So it is actually sigma L here, and this is J, and here it is E star. So it is a mixed diagram of excitation energy and angular momentum. Now this triangular distribution of the compound nucleus in excitation energy and angular momentum space will be now emitting, this has dissipated its energy, and what it will dissipate by emission of particles. So neutrons, it could be neutrons. For heavy nucleus, proton alpha emission is not favored much because there is a emission barrier, and so the particles, the residual nucleus that are formed, if you see A plus A going to C, going to B plus B. So these are the states of the B, that is the residual nucleus will have certain angular momentum, and when you have a nucleus with some angular momentum, certain energy is tied up in its rotational energy. So the rotational energy is given by h cross upon 2I, I is the moment of inertia, into J plus 1, where J are the angular momentum. So this states of different EJ values. As a function of J, certain energy is tied up in rotation. This is called the erased line. So you cannot have a level nucleus with this energy in the below the erased line. So energy has to be more than the erased line. So if when it is populating, when emitting neutrons, let us say, then it will come to this energy state. It will populate in EJ plane. This is EJ plane. Thus, this population will lead to certain population in the residual nucleus, and there is a called the drip line. That means this gap is called the binding energy. That means if you populate the nucleus here, then this cannot emit neutron. Whereas this, if you populate here, it can emit neutron because excess energy is more than binding energy. And so any population which will come in this erased band will be now due to the particular product. So 1n. If you recall the excitation function, 1n, 2n, 3n are bounded. This population now is frozen to 1n product. Similarly, and this is emitting, this population is frozen to 2n product, and so on. So in the angular momentum space, different product nuclei, the evaporation residues, are formed as compound nucleus is emitting 1 neutron, this product is formed, 2 neutron, this is formed, 3 neutron, this is formed. And similarly for protons and alpha can also take place. So once it is in this domain below the binding energy, now this nucleus are still excited, they will be emitting now gamma rays. And by emission of gamma ray, they come to their ground state, and that's what we say when we measure the cross section for a evaporation residue. This is formed by 1n, means this nucleus could not further de-excite because this has come below the binding energy of neutron in that particular nucleus. So this is the schematic of explaining how the evaporation of particles lead to different residues and the competition. In fact, what is actually known is that if a nucleus can emit particle, it will favor particle emission than gamma emission. Why? Because the gamma ray cannot carry much angular momentum. Gamma ray will carry 1 or 2 spins, whereas the particles can carry much higher amount of angular momentum. So particle emission is favored for high angular momentum states, provided excitation energy is more than the binding energy of the particular particle in the compound nucleus. In fact, if the excitation energy is very high, fission is the first predominant reaction, but fission has got a barrier. So if fission is possible, first is the fission, then particle emission, and then the gamma emission. That is the sequence. So if E star is more than binding energy, particle is favored. If E star less than binding energy, gamma is the only mode. Along the erased band, now in this band, this is called the erased band. Along the erased band, only gamma emission is possible, but particle emission not possible. Only above the erased band, states can emit particles. So what are the signature of the compound nucleus mechanism? I try to explain. First one I already explained, the Maxwellian nature of the particle spectra, and that is coming from, so the number of particles having energy E upon, so this is the kinetic energy of the particle, and number of particles will be having a Maxwellian nature. This is a typical signature of compound nucleus. This is the term, pre-exponential term, and e raised to minus epsilon upon t. So from the slope of this, in fact, you can find out what is the temperature of this compound nucleus that is emitting these particles. And the second important signature of the compound nucleus formation is forward-backward symmetric angular distribution of particles. So as if you recall, the compound nucleus emission does not know what way it was formed. It loses the memory of its formation. I recall the experiment by Ghoshal that the two reaction channels, a same product formed by two reaction channels, cross sections are same. And so if the cross sections are, if they does not know the memory of the previous interchannel, then we can say that the emission of particle is isotropic because there is no preferred direction. So the angular distribution we call d sigma by d theta. At a particular theta, there is the same number of particles at all angles. So d sigma by d theta is equal to constant. and I try to explain what does it translate into angular distribution. So I try to give here like this is a sphere. At any theta, the cross section is same, d sigma by d theta. So let us take a particular theta here, and at this theta you have a disk. So that is a disk of same theta. So you try to find out the solid angle, because what you essentially measure is the d sigma by d omega. You are plotting here d sigma by d omega, where d omega is the solid angle subtended by this strip. So it is a strip of the sphere which is solid angle having the same angle theta. So how do you know the solid angle? Solid angle subtended by a sphere at this point is 4 pi. The surface area of the sphere 4 pi r square upon r square, that is the solid angle 4 pi. So this solid angle by this strip of the sphere will be area of this. So it's like a circle into the strip. So it is like this actually. And so you have this is a circular strip. To see the cross section, this is this one, pi r square, but r is now r sine theta. So this is r sine theta. So 2 pi r sine theta, which is the circumference of this strip into the thickness of the strip r d theta. So this is the area of this strip, if you see from this side. And so this strip is a part of that sphere, 2 pi r sine theta into r d theta upon r square, the solid angle subtended by this strip at this point. And so it becomes, if you say d sigma by d omega will be d sigma by d omega into d omega by d theta will be 1 upon sine theta. And so the angular distribution as a function of per unit solid angle follows, this is what is 1 by sine theta graph. So more than the sine theta graph, because it is not always 1 by sine theta, it is more of forward backward symmetry, because the angular momentum can change this 1 by sine theta difference. Most important aspect is that forward backward symmetry. Whatever number of particles are emitted in forward angle, same number of particles are emitted in the backward angle. And so this forward backward symmetry is a signature of the compound nucleus. So Maxwellian nature of the particle spectra and the forward backward angular distributions, these are the two signatures of compound nucleus. So I try to give you some examples of the compound nucleus evaporation particle spectra. This is our own paper of 1997. So fluorine plus niobium giving rise to 112 tin. The alpha particle spectra you see here, Maxwellian nature. This is for protons, this is for alpha. So this is a clear-cut signature of a compound nucleus decay. This is how the nuclear physics community, nuclear chemistry community will verify this particular reaction follows the compound nucleus mechanism if the particle spectra are Maxwellian in nature. Similarly, the angular distribution of evaporation particles, forward backward symmetry as a function of theta, or even you can write cos theta, then whatever particles are then forward is symmetric in the both the hemispheres. So again, the forward backward symmetric angular distributions and Maxwellian nature of particle spectra are signature of compound nucleus reaction. Okay, so lastly, I do not have time to discuss the compound nuclear reaction mechanism, but just I wanted to tell you that this is not the complete story. The compound, other than compound nuclear formation, there are many other mechanisms, particularly when you go to heavy projectiles like carbon-12, oxygen-16, neon-20, and so on. So when you have a heavy ion as a projectile, the heavy ion induced reactions, the nuclear potential plays an important role. The angular momentum plays an important role apart from the Coulomb barrier. And so you will see the nuclear potential, the Coulomb potential the Coulomb potential is anyway there, but there will be one more called centrifugal BL, centrifugal potential barrier also will contribute. And so the fusion of the projectile target gets limited. So in addition to the complete fusion, there are non-compound nuclear reactions like incomplete fusion, deep inelastic collision, fast fission, and so many other reactions open up. So heavy ion reactions is a domain of research to study what are the reactions that do not follow a complete fusion. So that 2L plus 1 distribution, if you recall, sigma L versus L, complete fusion is this compound nucleus part. In addition to that, there are competing modes of incomplete fusion, deep inelastic collision, and quasi-elastic transfer. So elastic reactions, so they all encompass non-compound nuclear reactions, and there is so much of research actually open for the nuclear chemistry or nuclear physics community to study the limitations of nuclear compound nucleus fusion reactions. Just if I have time, let me see. We have in fact done some experiments on incomplete fusion reactions. That means a same compound, same product can be formed by complete fusion as well as incomplete fusion reactions. So these incomplete fusion reactions are similar to complete fusion reactions, but their momentum transfer is different. Linear momentum transfer in the formation of the same product is different. That we have tried to find out by measuring the range of the recoils. So this is the recoil range distribution of evaporative residues found in the formation of these products. So the complete fusion products are stopped at much later part of the recoil range scheme than the incomplete fusion. Means the kinetic energy of the recoils, the products that are formed, is much higher for the complete fusion than for incomplete fusion. That is reflected in there. So this is the momentum, this is essentially the range of the particle in the aluminum. These are the compound nucleus products, but the non-compound nucleus products have got the lower range. So the momentum transfer is not complete for incomplete fusion reactions. That is revealed in the recoil range distribution of the evaporation residues. So I wanted to just give you a glimpse of what are the different reaction mechanisms other than compound nucleus. You see them all opening up in heavy ion induced reactions. So I will stop here and then discuss the later part subsequently in the next lecture about the nuclear fission and nuclear fusion reactions. Thank you very much.